So if we are tasked with graphing a polynomial function, we need a process to be able to make that happen. So we have to find the zeros. We have to know what the endpoint behavior is. Does the graph take off to positive or negative infinity? We need to have all that information to be able to sketch the graph. So we're going to start with the zeros. So we have our rational zeros test. We come up with a list of possible places that the graph could be crossing through the x-axis. So we go from infinity locations, it could literally be anywhere, and we narrow it down using that rational zeros test. So once we've done that, then we're going to systematically test those possible zeros to find them, find the locations where the graph crosses through the x-axis using synthetic division and then later factoring. Because once we've gotten it down to a quadratic, as we'll see, we don't want to keep on using synthetic division. We can go ahead and factor to find those remaining zeros or other algebraic techniques. So once we find all the zeros, once we find all the places where the graph crosses through the x-axis, then we can use the leading coefficient test to figure out is the graph shooting up to positive infinity or down to negative infinity after it's done doing what it's going to do in the middle part of the graph. So remember, the leading coefficient test doesn't tell us anything about the middle. That's what doing all the zeros work is about. But ultimately, the graph is eventually going to take off up or down to positive or negative infinity. And so the leading coefficient test tells us that. And then lastly, as necessary, we can plot some points to find estimates of the local maximum and local minimum locations. And so using this process, we can piece together the graph of a polynomial function. So let's put that plan into action with this first example. So again, we have to generate a list of possible rational zeros using our rational zeros test. So that's our P over Q list. So recall that our factors for the top are going to be everything that divides evenly into 15. So we're going to have plus or minus 15, plus or minus 5, plus or minus 3, and plus or minus 1. And then in the bottom, it's the factors of that leading coefficient, so 1, so plus or minus 1. So our laundry list, if we put it in order, it's going to be from negative 15 down to negative 5, negative 3, and negative 1. And then the positives, 1, 3, 5, and 15. So again, we have 8 possible rational zeros that we have to work through. And so now we just have to start testing them out. So the way we're going to test them is by using synthetic division. Because if you'll recall, if something is a zero of a polynomial function, then you're going to get a remainder of 0 when you perform synthetic division. So we'll set on the inside our coefficients. So we can set 1, negative 8, 14, 8, and negative 15. There are no terms that are skipped, so no zeros for placeholders. And then we just need to pick one of the numbers from our list. And so I generally lean to picking something either in the middle of the positives or the middle of the negatives. And so in this case, just out of random chance, I'm going to try 3. There's no real good predictive way to approach this other than to just try a number and see if it works. So if we roll through our synthetic division, remember we bring down the 1 there, and then I multiply on the diagonals. So 3 times 1 is 3. So I add, I get negative 5. 3 times negative 5 is negative 15. I add in the vertical direction, I get negative 1. 3 times negative 1 is negative 3. I add in the vertical direction and get 5. 3 times 5 is 15. And so I have indeed lucked out. I found a 0. So now in my list of zeros for this polynomial function, I know one of them, and we know that there are going to be 4. Let's try to make that look like a circle there. We know that there's going to be 4, so we've got 3 is one of our zeros, so I can right away go to the x-axis and put a dot at 3. I know my graph's going to cross through that location. But I still have 3 more that I need to find. And so I'm going to need to use synthetic division again, but I'm not going to go back to the original function. I'm going to take advantage of what I've already done, and I'm going to divide into this remaining polynomial. Remember, these are coefficients of a polynomial that divides evenly into our original function. So if something is going to be a 0 of the original function, it's also going to be a 0 of what we see here. And the other thing that I can do is, now my last number in my polynomial function that I'm finding zeros for is a 5 instead of a 15. So that means I can cross off some numbers from my list. So 15 and 3 are no longer candidates because they don't divide evenly into 5. Likewise, 3 and positive 15 are no longer candidates because we're working with this polynomial function that would be x cubed minus 5x squared minus x plus 5. So if we were to regenerate our p over q list, it would only be 5 and 1 that divides evenly into that last number. So from our reduced list of options, let's try 5 as a 0. So I bring down the 1, multiply on the diagonal, so I get 5, add in the vertical direction, I get 0, 5 times 0 is 0, negative 1 plus 0 is negative 1, 5 times negative 1 is negative 5, and then I get 0 as a remainder. So we lucked out both times, and we had an option that worked again. If we test something and we don't get a 0, then we just have to go back and try a new number, but we can eliminate that number that we did try from the list. And we also get the bonus piece of information that whatever we tried, that would be the input, the x-coordinate, to go along with that output. So I wanted to make mention of that. But in this case, we found 5 as a 0 as well. So that means my graph is going to go through 5 on the x-axis. But I still have 2 more zeros to find. But fortunately at this point, I don't need to use guess and check with synthetic division anymore, because now I can take advantage of this answer right here. So remember, this was the coefficient in front of x to the 4th, then we knocked it down to x to the 3rd, and then with another round of synthetic division, we knocked it down to x squared. So what we have left here is the coefficients in front of a quadratic, x squared plus 0x, and then minus 1 equals 0. And so this now we can use to find our remaining zeros. We can factor this. We can solve using square roots. We have options. So I've got x plus 1 times x minus 1 equals 0. So I just take this equation, set it equal to 0, and then I just need to solve. So I'm going to set x plus 1 equal to 0 and x minus 1 equal to 0. And so then I just get 1 and negative 1 as my remaining 2 zeros. So 1 and negative 1. And so I can put those locations on my graph. And so now I have found the 4 zeros. I have located all the places that my graph is going to cross through the x-axis. But I still need to piece together the rest of the graph. I need to know whether it's going up to positive or negative infinity, and then I need to have an idea of what's going on in between all these zeros. So for the leading coefficient test, I know that I've got a touchdown graph because the highest exponent is even, and with a positive leading coefficient, I know that both sides of my graph are going to take off and go up. So that means after my graph crosses through the x-axis for the last time, it's going to take off and go to positive infinity. So on the right-hand side, the last time it crosses through the x-axis is right here at 5. So that means from here, it's got to be shooting up to positive infinity. And the same thing is true after it crosses through the x-axis for the last time over here on the left-hand side. It's got to be shooting up to positive infinity. It can't make another U-turn and go down and cross through the x-axis again because we have already found all of the zeros. They're at negative 1, 1, 3, and 5. So then we just have to fill in the gaps that are in between these zeros. And so I need to plug in the number that's halfway in between the zeros to figure out an approximate. It's not always exactly the right maximum or minimum, but it gives us a pretty good approximation. So in this case here, I can go ahead and plug in 0 for x, and so that's going to give us the y-intercept of negative 15. So clearly my graph only goes to 10 and negative 10 in the vertical direction, so I'm going to have to adjust my scale. So I'm going to count by 2's instead of by 1, so I'm going to make this 20 at the top and negative 20 on the bottom. So if I have a y-intercept of negative 15, so halfway it would be 10, 12, 14, so that puts us right about here. So we can stay with the blue color there. So my graph is going to dip down here, it's going to come back up, and then again I can plug in a number halfway in between the next two zeros. That's going to be 2. Now I could either plug in 2, make x equal 2 and plug that in everywhere, or the faster way that we learned from the remainder theorem is I could use synthetic division to figure out what I get when I plug in 2. So instead of doing 2 to the 4th minus 8 times 2 to the 3rd plus 14 times 2 squared, I can go ahead and use synthetic division. So if I set that up, and I do have to go back to my original function, we've got 14, 8, and negative 15, we can roll through some quick synthetic division to figure out what that maximum point is going to be in between those two zeros. So 1 times 2 is 2, negative 8 plus 2 is negative 6, negative 12 after I multiply, 2 times 2 is 4, 8 times 4, or 8 plus 4 is 12, 2 times 12 is 24, negative 15 plus 24 is 9. So this is my remainder, and so therefore my graph goes through the point 2, 9. So I'm going to go over 2, up 9. Remember, we're counting by 2s, so that puts us right about there. So my graph tops out about here, comes back down again, and then I've got to figure out what that last spot's going to be. So I can use the same process. This time, though, I'm going to plug in 4. I'm going to divide by 4, halfway in between 3 and 4. So just to clear some space here, let me do a little erasing. Oops, we could have kept those. We can erase these. And so now we can go ahead and divide by 4. So those early coefficients were 1 and negative 8. I'm going to need to divide these, or erase these as well. And so I go through that same process. So I've got 1, 4 times 1 is 4. I get negative 4 when I add, negative 16 when I multiply, negative 2 when I add, negative 8. Add those together, I get 0. 4 times 0 is 0. And my remainder here is negative 15. So now, similar to when we crossed through the y-axis, I've got negative 15 as my bottommost point, so it's going to be about the same place right here. And so we've now pieced together the graph of this function. So to review, we started with our P over Q list. We found what the list of possible zeros were. And then we just had to start testing numbers. So we do that via synthetic division. I picked positive 3 as my first number, and I got lucky. I got a remainder of 0. That told me that I've got a 0. I know my graph crosses through the x-axis at 3. Then I needed to continue finding zeros using synthetic division, but because I was able to use this answer that I got when 3 worked, I was able to narrow down my options as to what were possible zeros, because now the last number in my polynomial was 5 rather than 15. And so I tested 5, and I got lucky again. We got 0 as a remainder. And then once we've got it knocked down to being a quadratic, so in the case of an x to the 4th polynomial, we've got to find 2 zeros via synthetic division. If it was x cubed, we would have only had to use synthetic division to find 1 0, because once we get it knocked down to a quadratic, we can use our quadratic techniques to find the zeros. And so I did that here. I set the remaining quadratic polynomial, x squared minus 1 equal to 0, and I solved by factoring to find the remaining 2 zeros. Then, once we've got those zeros plotted, we used our leading coefficient test to determine the touchdown or disco nature of the graph, and then more specifically which way the graph is going, up because of the positive coefficient. So that's how we got these pieces here. And then we just had to plot points to figure out how low and how high the graph went in between each of these zeros.